In this session, we'll discuss about 8086 microprocessor. Before going to discuss the internal architecture of 8086, let us see what is a microprocessor. Here, micro indicates small in size, but whereas processor is a device which accepts the input and processes the inputs, which means it computes, so it performs some operations, it manipulates the inputs and then produces the output. So any device which is performing some task on the given inputs and producing the output will be considered as a processor, and that device size is very much small. So that is why it is called as a microprocessor. Okay, let us see what are the general blocks which are present inside a processor. Now here, this is the block diagram of a microprocessor. As you can see, there are three major blocks which are present inside this. One is arithmetic and logic unit, register arrays, and then control unit. Now here, arithmetic and logic unit is mainly responsible for performing any kind of arithmetic or logical operations like plus, minus, and, or, shift, and these kind of operations are performed by this ALU. And coming to these registers, registers are mainly used for holding the temporary information or temporary data. And there are some other registers which will be helping the processor to find out where actually the next instruction is present. Okay, so these are mainly used for holding the information. Okay, and coming to the control unit, as the name itself saying that control, so it is something like heart of this particular processor unit. Okay, now this is responsible for generating some signals, and based on those signals any of the blocks will be performing their task. Okay, if this particular control unit is failed, then complete processor would be failed. Okay, so these are the three major blocks which are present inside the microprocessor unit. Now let us see what is a memory. So as we know that memory is a storage device and which is mainly used for storing the information. Okay, and there are two major categories inside this memory, that is read-write memory as well as read-only memory. Now read-write memories are those memories to which we can program the data any number of times, to which we can also erase the data any number of times. But when it comes to read-only memory, we can write the data only during the manufacturing process. So those kind of memories are nothing but read-only memories. Okay, and inside this ROM there are many types of ROMs like flash ROM, which can be programmed any number of times. Those are the present generation ROMs. Okay, and if I take a memory device, now that memory device is provided with three types of lines like address lines, control lines, as well as the data lines. Okay, now these address lines are used for selecting one memory location out of these memory locations. Okay, these address lines are used for selecting one particular memory location, and these data lines are used for transferring the information to or from the memory device, and control lines are used for specifying the type of operation which we are going to carry out with this memory device. Okay, so now here the number of address lines depends on the size of this memory device. As now the number of address lines are 4, therefore the size of this particular memory device is 16 bytes. Okay, 2 power 4 will give you the size of this particular memory device. So 2 power n will give you the size of a particular memory device, where n is the number of address lines. Okay, so in that way we are going to calculate the number of address lines required for a particular memory device. Okay, and control lines will be like read, write, as well as chip select. If I'm going with a writable memory, writable as well as readable memory, then it will have something like read signal, write signal, as well as a chip select signal. But when you go with a read-only memory, then it will have only two control lines like read signal as well as a chip select signal. Okay, so here as we have 4 address lines, so it contains totally 16 memory locations, where each and every memory location capacity is of 8 bits. Why? Because here we have 8 data lines. Okay, now let us see what is an input and output device. Now input devices are nothing but the devices which will give the information to the processor from the external world will be considered as an input device, and the devices which will get the information from the processor to the external world will be considered as a output device, like switches, keypads, all these can be considered as input devices. LEDs, LCDs, motors, these can be considered as output devices. Now this is one system which is based on microprocessor. So here we have a microprocessor, and which is connected to input port, output port, along with ROM, and that is read and write memory. We can consider it as a RAM. Okay. Now all these peripherals, all these components are connected to this microprocessor with the help of one bus, and that bus is called as system bus. Now here system bus is mainly used for connecting different components of the computer to the processor. Okay. Now this completely makes, along with some other peripherals, that can make a complete computer. Okay. So in order to make a processor to act as a computer, then we have to add the peripherals externally. Okay, like memory peripherals or input output peripherals. Okay. Now let us see what is this system bus. Now bus is nothing but set of wires. Now there are three set of wires present inside this system bus. Those are address bus, data bus, and then control bus or is control lines. Now here address bus is unidirectional, which means the data can be flowing only from one way, that is can be flown only in one way, that is from the processor to the peripherals or processor to the external world. Okay. So here this address bus is used by the processor for selecting a particular peripheral or selecting a particular memory location inside the peripheral. Okay. Now coming to the data bus, this is bidirectional. Why? Because it carries the information to and from the processor. Okay. So that is why it is a bidirectional data bus. And control lines, now it is again a bidirectional bus, where it carries out with read, write timing signals, as well as some control signals are specified or control signals are generated by the processor, and peripherals are going to request the processor with the help of these control lines. Okay. So system bus is used for connecting different parts of the computer to the processor. So this is how we are going to connect the external peripherals to the processor with the help of address, data, as well as the control lines. As you can see here, there is one address bus which is connected to all the peripherals, but this is a unidirectional bus. It means processor can only generate the address and it will send the address to the peripherals through this address bus. Now that is received by all the other peripherals. But when it comes to data bus, it is a bidirectional. Why? Because processor can send the information to the peripherals, as well as it can also receive the information from the peripherals. So that is why it is a bidirectional bus. And there are read and write control signals. Along with these signals, we can also represent some other signals like request signals and acknowledgement signals. Okay. So this is how we can design a system which is based on a microprocessor by adding some external peripherals. Now let us see the features of 8086 processor. What kind of features that this particular processor is providing. Actually, this processor was designed by Intel. Now let us see what are those features. It is a 16-bit microprocessor. Now here 8086 is 16-bit, whereas coming to 8085, it is an 8-bit processor. Now what is the difference between 16-bit and 8-bit processor? Now 16-bit microprocessor can carry out a maximum of 16-bit operations. Okay, it can carry out a maximum of 16-bit operations, so that is why it is called as a 16-bit processor. Or else I can say that the capacity or capability of ALU is 16-bit. It can only go with a maximum of 16-bit operations. Okay, and 8086 has 20-bit address bus and can access up to 1 MB of memory. So as it is having 20 address lines, so it can access up to 1 MB of memory. Okay, so this 1 MB of memory can be interfaced to this 8086 processor. So 2 power 20 is nothing but 1 MB. Now it can support up to 64 kilo input output ports, 64K input output ports. We'll discuss about this particular feature when we come across 8255. And it provides 14 16-bit registers. Okay, as we have seen the block like registers inside the processor, so here it totally provides 14 registers, and the length of each and every register is 16-bit. Now word size in this particular processor is 16 bits. Okay, and double word here is nothing but 4 bytes. Okay, which is nothing but 32 bits. Now it has multiplexed address and data bus, that is from AD0 to AD15. A indicates address and D indicates data. Okay, so if one particular line is carrying multiple informations, then we can call it as multiplexed lines. So this AD0 to AD15 is called as multiplexed lines. Why? Because it can carry the address information as well as the data information. Okay, so there are a total of 16 data lines, and here we got 16 address lines, and remaining address lines are from A16 to A19. So a total of 20 address lines are obtained here, that is from A0 to A19, and 16 data lines from D0 to D15. Now 8086 is designed to operate in two modes, minimum and maximum. So it can operate in two modes, one is minimum mode and the other one is maximum mode. So we'll discuss it later. And it is also provided with one instruction byte queue, and whose size is 6 bytes. Okay, and it requires positive 5 volts power supply. So a maximum of 5 volts can be given to this processor. More than this would damage the processor or would damage the IC. Now it is a 40 pin DIP package, which is nothing but dual inline package, and address ranges from 50H to 5FH. Okay, now this will give you 1 MB of memory. Okay, whose starting address starts from 00000 and ending address is FFFFF. Okay, and memory is byte addressable. So here we can access the memory in byte format. We cannot access them in bitwise format. We can only access them in byte addressable manner. Okay, every byte has a separate address. So as every byte is having a separate address, so we can access them in a byte addressable manner. Okay, now this is the internal architecture of 8086 processor. As you can see here, this is the area where we actually interface the external memory to the microprocessor, that is 1 MB of external memory. Okay, now apart from this, now this complete architecture is divided into two parts. As you can see here, one part is named as BIU and the other one is named as EU. BIU is nothing but bus interface unit and EU is nothing but execution unit. Okay, now this BIU contains this adder. This is called as a address conversion mechanism adder, and some segment registers, and then the queue which we have discussed now, that is instruction byte queue, whose size is 6 bytes. As you can see here, 1 2 3 4 5 6. Okay, and a bus which is connecting all these blocks. Now coming to the EU, which is nothing but execution unit. Now it contains the general purpose registers along with some pointer and index registers, and it has arithmetic and logic unit, and then it has flags, which is nothing but a flag register, and then it has a control system where it generates the control, that is timing signals, as well as some decoding operations will be carried out by this control system. Okay, now let us see what actually this BIU performs. Okay, now here BIU is mainly responsible for handling the transactions with this memory. Okay, now this BIU is mainly responsible for handling the transactions with this memory device. Okay, it means initially what happens here is this segment registers along with some of these pointer registers as well as index registers would be generating an address. Okay, and that address is would be generating some address. Now that address will be calculated, or physical address will be calculated by this summer or adder. Okay, now what do you mean by physical address? Physical address is nothing but the location where actually the operand is resided. Okay, the exact location where actually the operand is resided. Now by adding these segment registers along with this pointer as well as index registers, now this this particular adder will be producing the physical address. Okay, now based on this physical address, now the processor is going to fetch the instruction which is provided in that particular address. Now that fetched instruction would be stored inside this instruction byte queue. Okay, so this is how it is going to carry out all the transactions with this particular memory device. Okay, now coming to the execution unit, now it takes the instructions, that is previously fetched instructions from the instruction byte queue, and those instructions are decoded into the understandable language of the processor, that is in hexadecimal or in binary format. Now after decoding operation, now the control system would be generating some signals. Now based on those signals, this arithmetic and logic unit is going to perform the operations on the data operands. Now after getting the result, that result would be stored inside any of these registers. Okay, and the status of this particular ALU will be represented by this flag register. Okay, now these are what the operations that an execution unit is going to carry out. Okay, as you can see here, BIU performs all bus operations such as instruction fetching, reading and writing operands from memory, and calculating the address of the memory operands. The instruction bytes are transferred to the instruction queue. Now it is going, execution unit is responsible for executing the instructions. Okay, now here both the BIU as well as the execution unit are asynchronous in nature, in the sense both are independent in nature. It means while as you can see here, while this BIU is fetching the instruction from the memory, now this execution unit will be executing the previously fetched instruction which is taken from this instruction byte queue. Okay, as it takes the instruction and it will be stored inside this queue, okay, from the one end, and from the other end this execution unit is going to retrieve that instruction and executes those instructions. So here simultaneous fetching as well as execution is going to happen. So that is why both are independent in nature. Okay, so as these are independent in nature, so it provides a possibility of pipelining. Okay, it provides the mechanism called as pipelining. Now what do you mean by pipelining? So pipelining is a technique where multiple instructions are overlapped in execution. Okay, it means while one instruction is in the fetching stage, now the previously fetched instruction would be in the execution stage. Okay, so here if we are using pipelining effectively, then it enhances the performance of the system, as well as the processor time is efficiently utilized. Okay, now BIU contains instruction queue, segment registers, instruction pointer, address adder. Okay, as we have seen now, and execution unit contains a control circuitry, instruction decoder, okay, which is inside this control circuitry, ALU, pointer and index registers along with the flag register. Okay, now let us see in detail of this execution unit. As you can see, this part will be considered as an execution unit. Okay, now it is responsible for decoding the instructions fetched by BIU, as just now we have discussed. Why? Because the instructions which are written by the user, okay, will be in high level language. Now while storing that information, it would be converted into the binary language, but it has to be converted into the language which is understandable to the processor. Okay, that is done by this decoder, and then it also generates control signals. Now based on those control signals, all the other peripherals would be working. Okay, and then executes the instructions. So by understanding the instruction, it will perform a particular task which is specified by the user. That is nothing but execution. Okay, now these are the blocks which are present inside the execution unit. Now apart from those things, execution unit also contains this part, which is nothing but general purpose registers as well as pointer as well as index registers. Okay, now it has a total of 4 general purpose registers like AX, BX and CX and DX. Now all these registers, that is AX, BX, CX and DX, can be accessed with 8-bit pairs. Okay, and their names are given as AH and AL, so they can be accessed with the name AH and AL, or BH and BL, CH and CL, or DH and DL, or else they can be accessed with their 16-bit register names like AX, BX, CX and DX. Okay, now here AX is nothing but accumulator, BX is a base register, CX is count register, and then DX is a data register. Now here AX is mainly used for holding the result in case of multiplication and division operations. Okay, and it can also be used by some of the instructions as a implicit operand. Okay, and this is mainly used in input output transactions. Okay, this register is mainly used in input output transactions. Okay, now coming to the BX, it is called as base register, which is used for holding the temporary information. Okay, and it can also be used for holding some offset address in case of some addressing modes. Okay, so for now just keep it in mind that BX is used for holding information along with the offset address. Okay, now coming to CX, it is used for holding the count in case of iterations. When we are going with executing an instruction for multiple times, then we are going to use this particular CX register as a count register. Okay, so it can be addressed with CH or CL. Okay, and then DX is a data register, which is again used for holding the temporary data, as well as this DX register is called as extended accumulator. Okay, whenever the AX is insufficient for holding the result, now the extra result would be stored inside this DX. So that is why it is called as extended accumulator. Okay, and this register is also used in case of input output transaction, that is input output port transactions. Okay, now all these registers can be accessed or can be used with 16-bit names like AX, BX, CX and DX, or else they can be accessed with their 8-bit names like AH, AL, BH, BL, CH, CL and DH, DL. Okay, H indicates higher byte and L indicates lower byte. Okay, now apart from these registers, it also contains pointer as well as index registers. Okay, now we'll see what is this pointer and index registers. Now AX, word multiply, word divide or word input output. When we are carrying out multiplication of two words or dividing two words or word input output operations, then we have to use AX register. Okay, for byte multiplication, byte division, byte input output as well as decimal arithmetic, we have to use AL register. In the same way, AX that is AH, and BX for storing the address information. As I told you that it is used for holding the offset information or offset address. Now CX for in case of string operations where we carry out some iterations, so that is why we use CX register, and CL is for used for shifting and rotation operations, and DX is used for holding some input output address during input output port transactions. Okay, now let us see those pointer and index registers. Okay, now stack pointer. Here stack pointer is used for holding the offset information or offset address. Okay, offset address of the stack. Okay, it is mainly used for holding the offset address of the stack. If we are carrying out some operations with the stack, okay, now if we want to locate an operand which is present inside the stack, then that particular operand physical address or the exact location is obtained by adding the value present in stack segment register along with stack pointer. We'll discuss what is that stack segment register, but the physical address of any operand which is resided in the stack will be obtained by adding the stack segment register along with stack pointer. Okay, so stack pointer is used for holding the offset address of the stack. Okay, and this base pointer is again similar to the stack pointer. It is also used for holding the offset address of the stack. Okay, we can also get the physical address by adding base pointer with the stack segment register, but the only difference here is it points to top of stack and points to bottom of the stack. Now let us see what is this source index and destination index registers. Okay, now here source index register is used for holding the offset address of the data segment. Okay, now here the length of this source index register is 16-bit. Okay, it is used for holding the offset of the data segment. Okay, so whenever we are giving some inputs to the processor, those inputs are stored inside one particular segment that is called as data segment, and any operand which is resided inside this data segment is accessed by adding the content of data segment register along with source index register. Okay, now here coming to the destination index, which is again of 16 bits. Now whenever we are getting the output, now outputs are stored inside this extra segment. There is one segment whose name is extra segment where actually the outputs are located. So if you want to find out the physical address of an operand which is resided inside this extra segment, then we have to add the content of extra segment register along with this DI register, which will give us the physical address of the operand which is resided inside the extra segment. Okay, now here the SI and DI registers may also be used to access data stored in arrays. Okay, now we have one more block inside that execution unit, that is flag register. Now flag register is mainly used for representing the current state of the processor. Okay, it will represent the current status of the processor, as well as it is used for controlling the operations of the processor. Okay, it will represent the status, as well as we can also control some of the operations carried out by the processor. Okay, now it is a 16-bit register, but out of these 16 bits only 9 bits are active, which is nothing but only 9 bits are used, and remaining 7 bits are undefined, which is nothing but they are reserved for the future purpose. Okay, now these 9 flags, are classified as two more flags, that is status flags and then control flags. Status flags for representing the status of the processor, and control flags, as the name saying, that control. So by using this we can control some of the operations carried out by the processor. Okay, now as you can see here, here it is the flag register, and this is the MSB, and this is the LSB. Okay, U indicates undefined or else unused bits or else reserved bits. Okay, now here OF, overflow, direction flag, interrupt flag, trap flag, sign flag, zero flag, and then auxiliary carry flag, parity flag, and then a carry flag. Okay, so here each and every bit is having its own importance. Okay, let us see what is the importance of each and every bit. Now carry flag. Now this particular bit will become 1 whenever there is a carry during the addition, or whenever there is a borrow during the subtraction operation. Okay, so if you are performing the addition or else subtraction operation, if you get a carry, then that particular carry or borrow will be stored inside this particular flag, indicating that a carry is generated or else a borrow is generated. Okay, coming to this parity flag, now here it will be set to 1 whenever the result contains even number of ones. Okay, so after some computation done by ALU, now the result would be stored inside one particular register. Okay, that register is AX. Okay, if you are storing the result in AX, if there are even number of ones in that particular result, then this particular PF will become 1, indicating that there are even number of ones inside the result, and it would become 0 when there are odd number of ones. Now auxiliary carry flag. Now this particular flag becomes 1 when there is a carry from the lower nibble to the higher nibble. Okay, if there is a carry from the lower nibble to the higher nibble, then this particular bit will become 1. Okay, and then so this flag is mainly used in case of BCD addition and subtraction. Now zero flag. Now after the arithmetic or logical operation, if the result obtained is 0, then this particular flag will become 1, indicating that the result is 0. Okay, and then sign flag. Now if the result is a negative, number, then this particular bit will become 1, indicating that the result is a negative number. Okay, if the result is positive, then it becomes 0. Okay, and this flag is considered when we are doing some signed operations like signed bit, signed addition, or signed subtraction. Now we have a trap flag. Now this can be programmed by the user. Okay, so if you are programming this to 1, then the processor enters into single step execution mode, which is also called as debugging mode. After executing each and every instruction, the processor will execute an ISR which is related to the trap routine or trap interrupt. Okay, now this is one of the control flag. Now we have interrupt flag. Again, this can be programmed by the user. If you are programming it to 1, it means you are disabling the interrupts which are coming through INTR pin. We'll discuss it later when we come across the pin diagram of 8086. Okay, so if this particular bit is 1, then all the interrupts which are coming through this INTR pin are enabled. Okay, if this is 0, it means all the interrupts are disabled. Okay, now we have direction flag. Now this is the last control flag. Now if this particular bit is 0, then it will be in a auto increment mode. If this is 1, then it will be in a auto decrement mode, and these modes are used in case of string operations. When we are carrying out some operations with the strings, then this direction flag will be used. Now trap flag, interrupt flag, as well as direction flag will be considered as the control flags. Okay, and they can be programmed by the user. And coming to the overflow flag, now this particular bit will become 1 or will become 0 or will be considered when we are performing signed bit addition or signed bit subtraction. Now this particular bit will become 1 when there is a carry from the 7th bit to the 8th bit in case of signed bit addition. Okay, and this bit will become 1 if there is a borrow from the 8th bit to the 7th bit during signed bit subtraction. Okay, now let us see an example where initially AL is the register which is holding a value 7F. As we know that all these registers will be holding the hexadecimal value, therefore 7F H indicates hexadecimal. Now I have written one instruction, ADD is nothing but add. Okay, add AL comma 1, where I am adding a hexadecimal value 1 to this AL register. It means the contents of AL register, that is 7F, is added with 1 and the result is again stored inside this AL. Okay, now after execution of this instruction, AL will be holding this value. 7F plus 1 is nothing but 80H. Now after this addition operation or after executing this instruction, okay, now all the status flags, let us see what actually the status flags are going to hold. Carry flag, as there is no carry, so this would become 0, and parity flag, now as you can see how many number of ones are present, only 1, which is nothing but odd number of ones, therefore PF is 0. Okay, and auxiliary carry flag, now there is a carry from the lower nibble to the higher nibble. What do you mean by nibble? Nibble is nothing but 4 bits. Okay, lower 4 bits, upper 4 bits. Lower 4 bits are called as lower nibble, higher 4 bits are called as upper nibble. Okay, now if there is a carry from the lower nibble to the higher nibble, then this particular bit will become 1. Okay, as this addition have generated a carry from the lower nibble to the higher nibble, so this has become 1. And then 0 flag, as the result is not equals to 0, therefore 0 flag would be 0. And then signed flag, now it has become 1. Okay, why? Because the 8th bit, that is the MSB, is 1. Okay, and then overflow flag, now it is again 1. Okay, why? Because the sign bit has changed. Okay, so this is how all the flags are going to represent the status of a particular execution. Now let us see bus interface unit. Now inside this bus interface unit, we have a instruction byte queue along with segment registers and then an adder. Okay, now out of these three, let us see instruction byte queue, and in the next session we'll discuss about these segment registers. Okay, now BIU is mainly responsible for implementing the pipeline architecture. Okay, why? Because it is initially fetching all the instructions and holding all the instructions which are fetched by the BIU. Now those instructions are again retrieved by execution unit for performing the execution on those instructions. Okay, so here it is a 6-byte queue. Okay, so from one end instructions will be stored, and from the other end execution unit is going to retrieve the instructions. Now the EU accesses the queue from the output end. It reads one instruction byte after the other from the output of the queue. The intervals of no bus activity which may occur between bus cycles are known as idle state. Okay, if the execution unit or if the bus interface unit is not doing any kind of operation, then those cycles are called as idle state. Okay, now in the next session we'll discuss about memory segmentation along with the segment registers. Thank you.